Archimedes Principle, Law of Buoyancy. The law of buoyancy, known as the Archimedes Principle, that was dated back 2,200 years to the Greek philosopher Archimedes. So legend says that the king of Syracuse, that is Hiero. So King Hiero suspected that his new gold crown maybe have been constructed of materials other than pure gold. So he was thinking it is made with other materials. So during his his suspicion that his crown were made of not pure gold. So he immediately calls to Archimedes to investigate, so to determine what happened, how to determine if the gold he's wearing, the new crown he's wearing, is made of pure gold. So that's why Archimedes is asked to test it to find out how to determine. So Archimedes probably made a lump of pure gold, so that is weighing as the crown. Then the lump was discovered to be way more in water than the crown weigh in water, so thereby proving to Archimedes that the crown that he is wearing now is not a pure gold. So they're using a fake material, because the fake material possesses a large volume to the weight as a gold, so hence it will displace more water. So that's why, and that is what we call the Archimedes Principle. So there is a buoyancy force on the object equal to the weight of the displaced liquid. So the principle of the displacement, we have statement that a body immersed in a fluid, so displaces an equal volume of the fluid and is buoyed up by a force equivalent to the weight of the displaced fluid. The buoyant force acts against the weight at its centroid. Now for the illustration here, so we have here a simple body that is submerged in the fluid. So explains the statement that a body immersed in a fluid displaces an equal volume of the fluid. So we have here the volume that emerged is equal to the volume that is being displaced. So we have here the VI, which is the volume emerged. Now it is equal to the volume being displaced. So the volume that is being displaced by this fluid, so volume of the fluid, so they are equal. Now it is being buoyed up by the weight of displaced fluid. Now we have here from the centroid, so we have your centroid here. I'm going to draw the center of the gravity, so naming that one. We have here the center of the gravity of our object, Shumingli. Now it is being buoyed. Now going back, it is being buoyed up by the weight of the displaced fluid. So the reaction of the buoyant force is also acting in the opposite direction. So we have your B here. Now our buoyant force is equal to the weight of the fluid, which is equal to the specific weight of the fluid times the volume of the fluid displaced, which is equal also to the specific weight of the fluid times the volume of the fluid, volume of the object being immersed. Okay. Now for equilibrium, the body floats, where the summation of our forces at vertical is equal to 0. So we have now your weight, which is acting downward. Then we have the opposite here acting, that will be your buoyant force. So we have your weight, which is now equal to your buoyant force. And one also condition we can establish it parameter if so if the weight is greater than the buoyant force, okay, so then the body accelerates or it sinks, so it goes down. Then we have your work, or let's say you have your weight that is minus your buoyant force. We have your F net, total force that acting. So we have the summation of your forces is now equal to the mass times your acceleration. So since we have that the weight of the fluid is greater than the buoyant force, so we have an acceleration sinking. So that will now at the equilibrium the body floats. So we have the volume of the object, total volume of the object here. So that will be the visible. So I'm gonna name this the volume of the object. That will be the visible. So at the equilibrium, we have your buoyant force is equal to the weight. Now the equation of our buoyant force, that will be the specific weight of the fluid times the volume of the object which is being immersed. So that one. Now the weight, we have the specific weight of the object times the volume of the object. Now to determine the percentage of the volume emerged, so we have the ratio of your volume, the object that is being merged, and it is divided by total volume of the whole volume of the object. Now we can express this one as the specific, where our volume, this one is equal also to the specific weight of the object divided by the specific weight of the fluid. Or we can express it also as the value of the specific weight, so that will be the density of the object times the gravity. Then we have the density of the fluid times the gravity, where your gravity is the same, so it will be cancelled out. So cancel out this one. So we have the density of object, it's the ratio of density of the object and density of the fluid. And we can also further expand our equation to the specific gravity, okay, of the object times that will be the density of the object. So that will be also the density of the water. Let's say density of water divided by the density, specific gravity of the fluid times the density of the water. So we have your common here, we have your common density here, which is density of the H2O. So we have the percentage of the volume that is being emerged ratio. Now sample problem. So an iceberg having a specific gravity of 0.92. So I'm gonna write that one or given to the problem. So for the given of the problem, okay, so we have the specific gravity of the iceberg. Okay, so let's say that will be the specific gravity of the ice. So that be 0.92. We have it given. And it is floating on salt water, so we have the specific gravity of our water, or seawater. That's it. I'm gonna need that as W, so that will be equal to 1.03. So if the volume of the iceberg above the water surface is 1000, so we have the volume of here that is not immersed. So volume of the object, or VI, so that will be volume of the surface. So I'm gonna name this BS as 1000. That will be cubic meter. So what is the total volume of the ice? So we have your unknown, we have your total volume of the ice. Okay, that will be the volume of, or let's say this is the volume of the object gonna change this one to volume of the ice. Okay, then we have the volume of that is exposed to the surface, Vs, plus the volume of the emerged ice. So as shown here in the description, that is the volume emerged. Okay, so this is the summation, that is volume surface plus your Bi. So we can express this your volume of the ice, that will be 1000. That will be cubic meter. So volume of the surface that is exposed plus your volume of the ice that is being merged. Assumingly, this is our iceberg here. So we have your weight that is being drawn down, and we have the buoyant force acting up, pushing the object going up and floating it. So using the equation here, we know that our buoyant force is equal to the weight, where the specific weight of the fluid is equal to, and this is multiplied by the volume of the object being emerged. Okay. And our weight, that will be the specific weight of the weight of the fluid, will be the specific weight of the object times the volume of the ice, so that we have your Bi here. So we can express this one as, and we all know that our density, specific weight of the fluid, can be expressed as the density. So that will be expressed as density of the fluid times the gravity. This is 1, 2. Density of the fluid times the gravity. Then we have the volume of the object being merged. Then also the density of the object times the gravity times the volume of the ice, or the volume of the iceberg. And we all know that the specific gravity, the equation for the specific gravity, so that will be the ratio of the density of the fluid, or density of the object, divided by density of the water. So if you have the density of the fluid, so we have the density of the fluid, that will be the specific gravity multiplied by the density of the water. So rewriting our equation from here, so we're going to transfer this one to this side. So we have specific gravity of the specific gravity of the water, multiplied by the density of, so this will be this is I'm going to change this one as SW to signify that one as a seawater. Now we're going to multiply by the density of the water, so that we cannot be confused. Then we have the volume of the object being emerged, which is equal to the specific gravity of the ice times the density of the water. Then we have the volume of the ice. So we can cancel now the density here on both sides, so we have your common here. Okay. And we can express our volume that is being emerged as equal to the specific gravity of the ice times the volume of the ice, divided by the specific gravity of the seawater. And from the equation here, we can substitute the Bi, the equation here, to get the values. So okay, so we have the volume of the ice is equal now to 1000 cubic meter, then plus the specific gravity of the ice, we have the volume of your ice, divided by the specific gravity of your seawater. So we have here, So substitute that in, we substitute the values of specific gravities here. So we have the volume of the ice is equal now to 1000. Okay. This is 1000 cubic meter plus the specific gravity, that will be 0.92 divided by 1.03 times the volume of the ice. So we can transfer that one on the other side. So we have your volume of the ice is equal to minus, so that will be minus 0.893. Okay, that will be the volume of the ice is equal to 1000 cubic meter. So 1 minus 0.893, we have value. So we have the value of 0.107, so that will be the volume of the ice is equal to 1000 cubic meter. So we have the volume of the ice is equal now to, so we have the volume of the ice which is equal to 9,000, okay, 9,345. So that will be cubic meter. So we have your answer here. Okay, so that will be the solution to the problem here. Okay, so that's it.